All right. Hello, everyone. Welcome to today's class. Today, we will continue to talk about supervised learning. We will talk about two models, random forest and logistic regression, regularized logistic regression. So first, take a look at random forest. Okay. So we are here. We're talking about machine learning and supervised learning. So last time we talked about decision tree, the first model. And today we'll start with random forest. Let's first load the data set. We will still use the primary data set, and we will do some initial cleaning and data transformation. We remove all of the observations with missing values in the response variable, and we also create a new variable, which is AF top, and then remove any observations with missing values in this new variable. And then we call it primary. Okay. And a brief review about the measure of impurity, Gini coefficient, and entropy. So Gini coefficient is a measure of impurity, and the formula to calculate the Gini is like this. C is the number of classes in the response variable. So it's 1 minus summation pi squared. If there are only two classes, then the formula will be reduced to this one. It's a quadratic function of p, where p can be defined as the class probability of one of the two classes. Entropy, the formula is like this: negative summation pi times log pi. It is also a measure of impurity. If there are two classes only, the entropy formula can be reduced to this format, this expression, where P is just usually defined as probability of Y equals 1. Y equals one of the categories if there are only two classes. All right. And we also created two functions, a confusion matrix function and a function to calculate the misclassification rate. To avoid repetitions, we can create these two functions by ourselves, right? So that we can use them to evaluate different models. All right, let's talk about random forests. So last time we talked about decision tree, right? A decision tree is a tree-like flowchart that assigns class labels to individual observations. And the random forest is a natural extension of decision tree models. So namely, a random forest is a collection of bootstrapped decision trees. Bootstrap decision trees. It's a forest of decision trees. So that's why it's called a random forest. And in our class, we will use this package, random forest package. Let's take a look how to construct a random forest. A few steps. First, we need to determine the values of two hyperparameters. We choose the number of decision trees to grow and the number of variables to consider at each split. So first is the size of the random forest. How many trees will be included? The parameter that will be used to control this parameter, this value is n tree, number of trees. And at the same time, there is another hyperparameter which is called m trie. We know that in a regular decision tree, at each node, the tree will consider all of the feature variables in the data set and pick the best one to do the split, right? But in a random forest, it's not like that. Right? It will only consider a small number of feature variables available in the data set. For example, suppose there are like 10 variables, 10 feature variables in the data set. If M try is equal to 3, then at each node, the algorithm will randomly choose 3 variables from these 10 variables. And then among these 3 variables, it will choose the best one to do the split. And after the split, in the next layer, it will do the same thing. Randomly select 3 variables to do the, and then among the 3, choose the best one to do the split. So namely, in a random forest, the decision trees are more random than a regular decision tree, because you see different nodes will use different set of feature variables. So 2 hyperparameters, N tree and M try. Let's choose these. Then randomly select rows of the data frame with replacement. Namely, we will create bootstrap samples from the training data set. So that's why it's called a bootstrap decision tree. Each tree is built on the bootstrap sample. And then build a decision tree on the resulting data set on the bootstrap sample. And then randomly select M-try variables from the data frame at each split. So this is the kind of the detail about creating a tree. And then lastly, repeat this procedure N tree times. That's it. That is how to construct a random forest. Basically, with the training data set, it will generate multiple bootstrap samples. For example, if we let N tree equals 100, then we will generate 100 bootstrap samples. Okay, and using each sample, we build a tree 1 all the way to tree 100 decision trees. And of course, each decision tree will follow this restriction. I use only M-try variables on each node. And then how to do prediction. Given a new observation, it will use each of these trees to do prediction. For example, if it is a classification problem, binary problem, it will predict the label Y1 hat, Y2 hat, all the way to Y100 hat. If it is a classification problem, the algorithm will just follow the majority rule, see which class has the most count or frequency. And then that is a predicted label. For example, among them, 69, we have 69 ones and 31 zeros. Then the predicted label for that observation will be 1. Y hat will be 1 overall, using the random forest. Right? So that is how a random forest is constructed and how we use a random forest to do prediction. Now let's see how to construct a tree using the package. We'll first load the package, and then let's do a few things. So first, we drop all of the missing observations with any missing values. Right? This is because random forests cannot take any missing values, cannot handle any missing values. And we'll also convert the categorical variables into factor variables. So this is also a requirement for random forests, the random forest model in Google's package. So we do some simple transformation, and then split the data, right? And then specify a big formula. Basically, we will include all of the possible features, all of the features that we can use to build a model, call it formula for. And then we can start to feed the model, call the random forest function, specify the formula and the data set, right? Train 1 is this one, right? And then specify the number of trees and the number of variables considered at each node. Let's use 1005 for now. And then we can save the result in mod forest and print out the output. So this is the default output of the random forest model. So it shows you the number of trees and number of variables tried at each split. And it also shows you something else, right? OOB estimate of error rate. So this is out of sample, out of bag estimate of the prediction error. We'll talk about it a little later. So first you can look at the two hyperparameters and tree. So in principle, the larger the better for this hyperparameter, because a larger entry value will make the tree, the random forest more robust by reducing overfitting, because you have more like estimators in your random forest. So consequently, the result will be more reliable and less restrictive, more robust. However, if entry is too big, there are diminishing returns, and more trees need more memory and more time to run, to train. It will take a long time to run a random forest if entry is too big. Right? So usually it will let it be like 100, 500, 1000, etc. Depends on the size of your data set. If you have a very small data set, then you can use a very big entry value. And mtry determines how random each tree is. The smaller the mtry value is, the more random the tree will be. Okay, the larger the mtry value, the more complex the tree will be. So it's more likely to overfit. So in general, it's a good rule of thumb to use the default values. For classification models, namely if the response variable is categorical, then the mtry value, the default value is square root of the total number of feature variables, namely the total number of terms in your formula. Okay. And for a regression model, mtry is directly equal to the number of features. So these are the default values. However, you still have the option to tune this hyperparameter. The default option might not be the best, might not be the optimal. We can definitely tune this hyperparameter. And lastly, OOB estimates. So this is a mean prediction error on each training sample, using only the trees that did not have xi in the bootstrap sample. Remember, in a random forest, each decision tree is a bootstrap tree. Right? So the tree is built on the bootstrap sample of the training data set. Bootstrap sample uses a sampling with replacement, so there are repeated values. Consequently, some of the observations in the training set are not used in the training process of any tree, of each tree. Right? So let's take a closer look at here. So first of all, this OOB estimate is the mean prediction error on each training sample, using only the trees that did not have observation I in the bootstrap sample. So this is very easy to understand, right? And out of bag error rate is a valid estimate of the prediction error rate. So for example, if you separate the data, we actually separate the data to two parts, training and test set, right? So the OOB estimate is, in theory, very close to the prediction error rate for the test set. They should be very close. although they might be a little bit different. OOB might be smaller, slightly smaller than the test error, true test error, but they should be very close. So let's see more details about this term. So on average, each backed tree makes use of around 2/3 of the observations. So let's see how this claim is developed or made. Sort of prove it. Let's consider this probability. Probability of xi is not chosen by a bootstrap sample. What is this probability? So first, just focus on one observation, xi. What is the probability that it is not chosen by a particular bootstrap sample? It is 1/n, right? It is 1 minus 1/n. Yeah, it is 1 minus 1/n. The probability that it is chosen is 1/n. So probability that it is not chosen by a bootstrap sample is 1 minus 1/n. And then what is the probability that it is not chosen by any bootstrap sample? Remember, we have n bootstrap samples. Okay, so this is a total probability. Okay, so when n goes to infinity, this probability will approach e to the -1. Then consequently, overall, the probability that xi is chosen by a bootstrap sample will be 1 minus e to the -1, which is approximately equal to 0.63. So that's why we say, on average, each backed tree makes use of 2/3 of observations, about 2/3, and 1/3 will not be used at all. So the remaining 1/3 of the observations are referred to as out-of-bag observations. And we can predict the response for the ith observation using each of the trees in which that observation was out of bag. So for example, if we have 1,000 bootstrap, we build a random forest with 1,000 bootstrap trees, 1,000 bootstrap samples. And then for each observation, about these many trees has never seen this observation. So we can use these trees to do prediction for this observation. And then, so we will have like about 333 predicted values for this observation. And then we can either use the majority rule or taking average for regression problems to do prediction for this xi. And this is called out-of-bag prediction. Okay. So that's why for random forest, sometimes we say if you don't want to tune the hyperparameter, then you just want to estimate the prediction error or generalization error, then you don't have to use cross-validation or you don't have to split the data. Right? You can just fit a random forest on your entire training set or entire data set and use the OOB estimate to estimate the prediction error rate, even for out-of-sample observations. Okay. All right, now let's see how to tune hyperparameters. The random forest function package actually has a function that can help us to tune the m-try, this hyperparameter. So we used m-try equals 5 last time, but it might not be the optimal choice, right? So we can use this function, tune RF function. This one is used to tune hyperparameters, like m-try, right? However, this function is kind of, it is very demanding. It does not have a formula argument. Instead, it assumes that all of the variables in the X matrix will be used in the model. So in order to use this function to tune and try, we need to prepare our data again, right? So namely, we will create a new data set. I call it primary two, which is so by selecting all of the variables, including the feature variable and features variable in the formula and the response variable, which is window, right? And save the result in primary two, and then split the data, right? And then split X and Y for the training set. Right? Split X and Y. And then we are ready to tune the hyperparameter, right? Because this function is kind of picky, okay? You have to feed the entire data matrix, right? And it assumes that all of the columns in X will be used in the tuning process. So we specify X and Y, and then some other hyperparameters, right? Try start. So this is a starting value for try we want to consider. I will start from 2, at least 2, right? 1 is too too small. Okay? 1 means at each node we only consider 1 variable. Right? It start with 2. And step factor. So this is a factor that will be multiplied by start, right, to create the next value. So 2 times 2 will be 4. So the next value will be 4. And the next one will be 2 times 4 will be 8. Right? So this is a step factor. And then improve. This is related to the speed of converging. Okay. And then last one is entry try. So this one is the number of trees we want to try. We let it be 1,000. And save the result here and then print it out. Then 3 parts of information will be displayed. First one is the fitting process. Start with 2. Right? So it purely use out of bag estimate of error to determine the best model somehow. So in the first iteration, OOB is equal to 16.61%. And then it will actually divide 2 by the factor and let it be 1, go back. And this OOB error actually increased, right? And then search the next. And try equals 4. So increase it, right? Multiply 2 by 2. OOB error becomes 15.94. And then when it's equal to 8, and then it automatically creates this plot for you. So apparently, this is the optimal value for try because the out of bag error is minimized when try equals 8. And last one, summarize the result. Actually, I think when we run this, these 2 parts will be shown. And the last one is this object, best try. If you print it, you should see this summary table. So this is useful because it's fast and it does not use cross-validation. It just tune the model or try different values of try and calculate OOB error for each value. Right? So it's very fast and easy. Right? However, there is apparently one drawback, that is we cannot check the performance of the model for some values of try. For example, 3, 5, 6, 7, and all the numbers between 8 and 16 are not available. Right? So before we talk about how to tune it using some more strategies, let's take a look at this important concept in data science and machine learning. Variance bias trade-off. So the goal of tuning a machine learning model is to minimize the generalization error or the prediction error. The overall prediction error can be decomposed into three terms. So this is the overall prediction error. Y0 is the true value of Y, and F hat X0. This is the estimated value of Y or predicted value of Y using a model. We use F hat to denote the model because the model is constructed on random samples. So the model is also random. So it is a good estimate, probably is a good estimate of the true model, but it's not equal to the true model F. Suppose the true model is something like this. And then we can insert some terms into the square, minus, plus, and minus, plus, right? And eventually we can decompose this expected value of this square into these three terms. Okay? First one is sigma squared. So this is an irreducible error in the system. So this part, we cannot do anything about it. And the second part is the bias. That's the square of the bias. As you see, this is a bias. The expected value of the function minus the true function value. So the difference is called a bias. No matter how much you want to try, you try your best to tune a model. Unfortunately, probably the model is still biased. Right? The expected value is still not equal to the true function, true signal. This is the bias. And the third term is the variance. You see F hat minus expected value of F hat squared, E of it. So this is by definition the variance of F hat. This is the variance of your random model. All right, three terms. Remember, our goal is to minimize the whole thing. Minimize the sum of these two. This one, just forget about it, the sum of these two. And keep in mind that most models are distortions of the truth and hence are biased. So it's almost impossible to build an absolutely unbiased model. So all of the models are distortions of the truth. And picking the right model amounts to creating the right balance between bias and variance, so that the sum of these three terms will be minimized. So usually, so the prediction accuracy can be improved by shrinking or setting some coefficients to zero. So namely, you reduce the model. If you reduce the model, usually the bias will be increased, but the variance will be decreased. So that if we do so, we might be able to trade a little bias for a large reduction in the variance. So let's see this figure. This one shows you the concept of variance bias trade-off. And so using the relationship between bias and model complexity and the variance and model complexity. Okay. So as model complexity increases, for example, you add more X variables in your model, then the bias will decrease for sure. The bias will decrease for sure. It will be more and more specific and more and more close to the to the training data points. Okay, and no matter if signal or noise, but it will try to fit all of the variation in the training set. The bias can be decreased until to zero sometimes. And at the same time, the variance will increase. Variance will increase because the more specific your model is, the more variable your model is. It will become very rigid and unable to tolerate change in new observations. Okay. So apparently the sum of them is a total error, and it's a U-shaped curve usually. And finding the optimal model amounts to finding this split point of model complexity. So in all machine learning models, we always try to find this optimal point by tuning hyperparameters, to adjust the model so that the generalization error is minimized. The model might not be unbiased, but the prediction error is minimized. So usually we first decide a metric, usually not a metric, a loss function, and try to minimize the loss function. All right. So one technique to help us to find the optimal model is cross-validation. So let's take a look at what is cross-validation. Let's take a look at the simplest case, a two-fold cross-validation. So the idea of cross-validation is similar to that of Bootstrap. Repeat the training, testing, sampling 8 times. In a two-fold cross-validation, we separate the entire data set to 2 subsets with the same size, randomly split them, training and test set, same size. We can call them X1, no. We split the training set into 2 parts, X1 and X2, same number of observations. Then we first train the model using X1, and then calculate the error using X2, do prediction and calculate error using X2. Then we have an error rate, probably ER1. Then we reverse the rows of X1, X2. We feed the model using X2 and do prediction using X1, using the fitted model, and then calculate the error rate. We call it ER2. Then we take average, add them up, and divide by 2. So this is average error. And we repeat this process for different tuning parameter values and compare the average prediction error rate. So the whole process is for one value. For example, if you want to tune and try, we consider values from 1 to 10, right, for example. Then we start with try equals 1, right? And we do this two-fold cross-validation and calculate average rate, error rate, call it ER1. We do the same thing for try equals 2, etc., all the way to the last value, try equals 10. And then we'll compare this average prediction error rates and we'll find the smallest one and the corresponding try value. And that try value is the optimal try value. And for example, ERR5 is the smallest. Then the optimal try value is 5. Right. So this is how we use two-fold cross-validation to tune a hyperparameter. K-fold cross-validation is the generalization of two-fold. So, for example, in a 5-fold cross-validation, the training set is split to 5 subsets with the same size. And then in each trial, it will use one subset to do the validation or prediction, and the rest of them to train the data. And and we take turns to fit and do prediction and calculate the error rate. So in this case, for each try value, for example, for the first value, try equals 1, we will have 5 error rates now, because we will just take turns to use one piece as a test set, validation set, and the rest of them as a training set. And then take average of them to calculate the average error for try. So definitely this involves a lot of computation, and it takes a long time and effort usually. And usually K is chosen to be 5 or 10. It really depends on the size of your data set. And lastly, usually we use a one standard error rule. We pick the most parsimonious model within one standard error of the minimum average prediction error. So what does that mean? One standard error rule. For example, try equals 5 and try equals 6. So they have their misclassification error rates. For example, this is 0.012, this is 0.0110. It seems that this one is the optimal. It is the smallest, so we should definitely choose this one. But if we follow this one standard error rule, we will check if this one is within the one standard error of the most parsimonious model within one. So if this one is within the one standard error of the slightly smaller model than this one. So for example, if the one standard error region for try equals 5 is from 0.0909 to 0.011. So this value is within one standard error. Then it's recommended to just choose try equals 5. That's just because the entire process is random. It's random. So it's very likely that the small difference between these two error rates are just due to randomness. And if error 6 is within one standard error of error 5, that means they are not significantly different. In that case, we will choose to use the simpler model, the more parsimonious model, which is in this case try equals 5. So this is a whole idea. However, we may not have to follow this rule. Sometimes the cross-validation algorithm automatically use this rule or give you two options. You can choose the minimum. You can also choose the one that within one standard error of the minimum. For example, in the next session, we're going to talk about regularized logistic regression. You'll see that both of these two options will be provided. Anyway, let's move on. So previously we used TuneRF to tune try using the OOB error rate only, right? So now let's see in general how to use cross-validation to tune a hyperparameter in a machine learning model in R. The package we use is called Carrot. So this package. So this one provides an excellent facility to tune machine learning algorithm parameters. So it can be used for many different models. It's sort of like a generic tool. And however, the choice of parameters is left to the developer of the package. So for example, for random forest, the only tunable parameter is try. It does not allow you to tune tree. Um, so it is just authors or the developers' option, their choice. So we cannot change it. So different models have different set of hyperparameters that can be tuned using caret functions. So each one search is to define a grid of algorithm parameters to try. So if you want to tune one parameter, then you will create a one-dimensional vector of values to consider in a cross-validation. If you have two parameters to tune, then you will have a grid of values to try in a cross-validation. So for example, suppose parameter 1 we consider 3 values, and for parameter 2 we consider 3 values. And totally we will have 9 values to consider in the cross-validation process. Okay. So let's see how to tune our random forest first. First, load the package, caret, and then specify the method. There are two methods about cross-validation, right? Repeated CV or CV. Repeated CV allows you to do 2 or 3 times of multiple times of cross-validation. It's just because cross-validation is basically a random process. Right? It randomly splits the training data into a few folds, right? So it's kind of random. To make the result more robust to randomness, you can do multiple times. But usually, sometimes we just do it once. So let repeat equals 1. So this is the same with when we use method equals CV. A number is the number of folds. If we do 5-fold cross-validation, that number equals 5. And then search, we use the grid. Specify a random seed, right? And then this part expands the search space, right? Use expand.grid function to specify the search space for the parameter. Specify the parameter name, right? Don't forget this period, right? It uses dot syntax to specify the hyperparameter name, right? And then specify the values we want to consider. We want to consider even numbers between 2 and 16 inclusive. So call it tune grid. Then we're ready to train. Call the train function, specify the formula, right? 1 or 2 the period. So this means we will consider all of the features variables in train 2, right? Except for the response variable. Right? So 1 or 2 the period, we'll use all of the feature variables. And then specify the model, right? Method equals RF. That means we are tuning a random forest model. If you tune a decision tree or a large regression, you will use other methods. And metric. So this is the metric we use to evaluate the models. And then tune rate. We already specified the tune rate. The last one, control. So this one specified the cross-validation hyperparameters out here. Okay. All right, then let's see the output. So it shows you the number of samples in the training set, number of predictors, and the classes for the Y variable. And then let's see the result. 5-fold cross-validation repeated once. Summary of sample sizes. So basically, it tried the best to split the training set into 5 subsets with the same size. The first one has 1 less observation. And then this is the fitting process. It tried from 2 all the way to 16. So that is what we specify here, from 2 to 16, even numbers. And then it keeps track of the accuracy. You see increase, 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 and then decrease. And after 8, starts to decrease. And you can also choose to plot the result. And you see we save the result here in RF research. And we can just directly call the plot function to plot this. So apparently, it's very obvious that this is the maximum accuracy and the corresponding M try is 8 actually. Okay. All right. So this is how to use cross validation to tune a hyperparameter in random forest. Okay. All right. Then let's move on. Let's fit the optimal model using our random forest function that M try equals 8. Previously, M try equals 5, right? And then we create a confusion matrix and calculate a misclassification rate. So it's 18.71%. It's pretty good. It's pretty good. Remember, this is for out of sample prediction. We calculate the confusion matrix for the test set. And also this is the out of sample prediction misclassification rate, 18.7%. And after we talked about all of the classifiers, we will compare their performance, the performance of the optimal model in each family. Our last lecture about classification models. And notice that we use 23 variables to construct a random forest. And a natural question is which variables are influential on the response. We know that each decision tree in the random forest is a random tree, and at each node, it randomly selects a few variables, and at the end, choose one of them. Right? But the random forest keeps track of all of these records, okay? And it can return a quantity called importance. A quantity called mean decrease Gini to measure the importance of each variable. Right? So it's the mean decrease in Gini coefficient for each variable at different nodes. So we can take the result in mod forest, make it a data frame, and then row names to column. So just massage it a little bit, convert, change the dimension, and then arrange the result in descending order of mean decrease Gini. Turns out that AF prop is the most important factor, and then percent of high school graduate, and then percent of labor force, etc. So this is a very good way to figure out important variables or factors in a model. Although the random forest overall is like a black box, okay? You don't know what's going on, and you don't exactly know the relationship between each variable and the response variable. It's not like this decision tree. You actually can observe how the tree grows. Okay, but in the random forest, it's all black. You cannot see anything. But at least it can print out this importance list. Okay. And one thing that is interesting is you see the magnitude of this term, very big in the table. See, we know that Gini coefficient for two class problems, the Gini coefficient is between 0 and 0.5. So how can the mean decrease in Gini have so big values? So let's zoom in. So actually, let's see how the decrease in Gini is calculated. So let GT denotes the Gini impurity and node T. So this is node T, and the Gini coefficient value is GT. And then suppose we split GT into two nodes, then the left node and the right node. Okay, and we calculate the Gini for each node, then GL and GR. Okay. And suppose the left node has NL observations and the right node has NR observations. Then after the split, the overall Gini coefficient is the weighted average of the left node and right node. And the weight is the proportion of observations in each node. Okay. Notice that the sum of NL and NR is N, which is the total number of observations in the above node, in GT. And the decrease in Gini impurity should be defined in this way. Right? The original GT minus the updated Gini, the overall, the weighted average of GL and GR. However, rather than using node proportions as weights, it just uses the node counts as weight. So namely, multiply each term by n. So this is the decrease in Gini for each variable. So that's why the magnitude is kind of large for the mean decrease in Gini term, because it uses count instead of proportion as the weights in the weighted average. All right. And notes about random forest. So first, it does not accept any missing values. So you must remove all the observations containing missing values, or you can choose to impute missing values. And then random forest only accepts categorical variables as factors. So that's why we use the transform function at the beginning to transform all of the categorical variables into factors. For example, even the response variable winner and also region, to convert them to factor variables first. Okay. All right, that's all about this model, random forest.